Okay, so here's the video where I'm going to prove that result, which is still missing. So it's up in the corner. So there it is. It's theorem 5.1, the equivalence of the three characterizations of convexity for differentiable functions. And in the lecture I was kind of confused, and now the proof is I have a complete proof of this here, and I'm going to present this in this short video. So the proof goes like this. Of course, there are many possibilities, but I'm going to prove it first. So do not argue in a circle, but say I would first prove the equivalence of 1 and 3. So direction from 1 to 3. Actually, I think it was probably already correct in the lecture, but anyway, so what we do is we take a lambda between 0 and 1, take the inequality, now I write it exactly as in the handout, the convexity inequality, 1 minus lambda f of lambda y plus 1 minus lambda x is smaller equal to lambda f of y plus 1 minus lambda f of x. We subtract f of x on both sides. If we subtract f of x, kind of this 1 goes, this 1 here goes away, and so we have this same here, lambda times y plus 1 minus lambda times x minus f of x. So if this 1 is gone here, we could factor out the lambda, then it's lambda times f of y minus f of x, and we divide by lambda and get smaller equal to f of y minus f of x. And then for lambda goes to 0, which is of course valid, we can make lambda as small as we like. This converges to the directional derivative, and in case of differentiability, at that point for lambda to 0, this goes to the point x, f of x, and then the directional derivative, then the direction to which this points is y minus x as we need it. Okay, so this is this direction. So okay, now we prove the direction 3 goes back to 1, showing the equivalence of 1 and 3. And 1 is convexity inequality, and 3 is the tangent inequality. So this goes like we said x lambda is lambda times x plus 1 minus lambda times y. And if we do this, we can note that x minus x lambda is actually equal to 1 minus lambda times x minus y. And on the other hand, y minus x lambda, so if you see this, just plug it in and factor out. Y minus x lambda, on the other hand, is equal to minus lambda x minus y. Same thing, if you subtract this x lambda from y, factoring out gives you this. So now we take the convexity, or the tangent inequalities at two different points. So in one point we take it, so writing f of x is larger than f of x lambda plus the derivative of x of f at x lambda, and then here we have to put an x minus x lambda. So that's the convexity inequality stated in 3 at the points y is equal x and x is equal x lambda. We do the same thing for y, but also with x lambda over here, and get gradient of f of x lambda y minus x lambda. Oh, here we should have an angle like that. And now we evaluate, or we plug in this term here and this term over there, and we end up with f of x lambda plus 1 minus lambda. So we factor this already out, or bring it in front of the inner product, gradient of f of x lambda times x minus y. And here we get again f of x lambda plus, no, it's not plus, because we get a minus lambda back here, and we get a minus out, so it's minus lambda gradient f of x lambda x minus y. Okay, so we call this inequality 1, this we call inequality 2, and what we now just do is we take lambda times inequality 1 plus 1 minus lambda times inequality 2. And that's it, or actually, because yeah, what does it give? On the left hand side we get lambda f of x plus 1 minus lambda f of y. Then we have these terms here, and lambda times this plus 1 minus lambda times this is exactly that, so it's larger than f of x lambda. And these two cancel. If we multiply this by lambda, we get 1 minus lambda times lambda, and here we get the same with the negative sign, so these two cancel, and that's it. And x lambda, remember, is this, so that was this direction actually. Okay, that's an equivalence of 1 and 3, and now the equivalence of 2 and 3. So this direction, 3 implies 2. We had that already. Yeah, it's very simple. It's again writing these inequality 2 times and adding these inequalities. I do it again here for completeness. F of x, f of y is larger or equal to f of x plus gradient f of x times y minus x, and the other way around, f of x is larger or equal to f of y plus gradient f of y x minus y, and just adding them leads to these things here, which cancel out, and we get 0 is larger or equal to, let's say, gradient f of x minus gradient f of y, and then here y minus x, which is the right inequality because we have to flip here once and then we have to flip the inequality sign. So this direction is also not that difficult. Okay, and then the last thing which remains, everything else, the last thing for these three inequality implications, this equivalence of these three statements is implication from 2 to 3, so from monotonicity back to the tangent inequality. Okay, and this is exactly, not exactly, this is as I started, but again, I think I messed up the order of variables. So what we do is we define h lambda as f of y plus lambda x minus y, and observe that h prime of lambda is actually the gradient f of y plus lambda x minus y. So, sorry, this should be a gradient here. The gradient inner product with x minus y. Exactly. Okay, fundamental theorem says f of first this is what you want to investigate, and the thing happens that this is h of 1 minus h of 0. And then fundamental theorem of calculus, again, fundamental theorem of calculus gives that this is the integral over h prime over lambda, and we plug that in, 0 to 1, gradient f of x of y plus lambda x minus y, inner product with x minus y over lambda. So what we do now is we subtract gradient of f at x minus times x minus y, so that we get here what we want, minus gradient of f of x minus y is equal to integral from 0 to 1, and as I did in the lecture, if we subtract that here on the right hand side 2, we can just put it in the integral because the integral is of length 1, and then it unites with this term here, and we get gradient of f of y plus lambda x minus y minus gradient f of x times x minus y d lambda. And it just remains to observe that this term here is positive by monotonicity, because this guy minus that guy is a positive multiple of this. So this thing here is larger or equal 0 by monotonicity. And this was this direction. Okay, so if I recall correctly, we also have to do the rest of the proof, because I kind of skipped this because I was confused up to now. Okay, let's do it now. So remaining things which I want to show is this thing with twice differentiability. So the thing on the strict inequalities, this is pretty clear from the investigations. Strict inequality goes through. But for twice differentiable, so f is C2, okay, the equivalence of positive stability for Hessian and second. So we say we show kind of the equivalence of the Hessian of f of x is positive definite is equivalent to 2, and 2 is the monotonicity. Okay, what we do is we take x tau is equal to x plus tau times s for some tau positive and some x and s. So what we then we use that if we take gradient f of x plus tau times s in a product with s. So we investigate a thing like this, and what happens if we take the derivative, takes the derivative with respect to tau. So what happens then here is that this guy here turns into a second derivative, of course, so the Hessian, and times the inner, by chain rule, basically the inner derivative is just s, and the inner product with s stays. Okay, we use this to get the following. We use monotonicity. 0 is smaller equal to the inner product of gradient of f of x tau minus gradient of f at x times x tau minus x. So this is always non-negative, and we need to divide it by tau squared. So what happens here is that this here is actually equal to s, can be seen here, and also it's again fundamental theorem of calculus. We can write this also as an integral over 1 minus tau times integral from 1 to tau over this is kind of what we use here is gradient of f, Hessian of f at x plus lambda s times s over lambda tau. There's a typo in here, I guess. No, that's true. That's lambda, and then we integrate over lambda, so that's correct. So, and here we know that these guys are always non-negative. No, sorry, this is what you want to show. It would be the other way around. No, here's like this. So we arrive at that, and you want to show this guy is positive here. But what we can now do is we let tau go to 0. And what happens here? If tau goes to 0, we have an integral of length tau. We divide by tau. This has to converge to the integrand at the point tau or lambda equals 0. So this converges for tau equals 0 to Hessian of f at x times s times s. And so hence this is non-negative. This was the one direction. So this is kind of this direction. And for the other, so if the Hessian is, so this is this direction. So, and if the Hessian is positive semi-definite, we use basically the fundamental theorem of calculus twice. So this is now, I just write it down. It's basically straightforward to see, but not pretty obvious at first glance. If we have a term like this, gradient f of x times y minus x, and we just now add a double integral from 1 to 0 and from 0 to 1 and from 0 to tau, and inside we have the Hessian of f at x plus lambda y minus x times, so this is still the Hessian, so times y minus x, and then we take the inner product with y minus x again and integrate that first over lambda and then over tau, and so on. You can check using fundamental theorem of calculus twice that this inequality is actually valid. Okay, so now by assumption we know that this here is non-negative because it's of the form Hessian at some point times the vector. So this is non-negative by positive semi-definiteness, and then actually we're already done. It's f of x plus gradient f of x times x minus y minus x. And this is what we wanted to show. And that is the complete proof. Thanks for listening.